Okay, good evening, everybody. Welcome to Cosmos from your couch. My name is Michael Reed, and I'm the Public Outreach Coordinator at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. And tonight we're going to be doing something a little bit different from what we often do in this series. Instead of a talk, we're going to be doing a purely open question and answer period where we're going to take as many questions as we can get through from you throughout up to the next hour. We'll see if you can keep us busy for an hour with questions. I think you can. We've got lots of questions already from different social media. You can ask whatever you like. Just try and keep your questions family friendly and respectful. You can type them into the chat on YouTube, and we'll pick them up there. And before we go to their questions, I'm going to introduce my colleagues here, and then we'll ask them a couple of questions so you can get to know a little bit about them. So we're joined tonight by Dr. Alana McDonald, Dr. Abigail Kreitz, and Dr. Renee Hlashek. So I'm going to ask each of them to just say a couple of words about themselves. And the first question I'm going to ask them is, what have you been working on lately? So we'll start with Dr. McDonald.
All right. What have I been working on lately? So a lot of my job in the astronomy department at the University of Toronto has to do with education and outreach. And a lot of the outreach I did was in person at the planetarium or at the observatory. So I've been filling that void by giving a lot of talks on the internet. Just this morning, in fact, I gave a talk to a bunch of apparently almost 1,000 children who were part of the University of Toronto community. So it was very rewarding. I talked about how gravity works, and that was really fun.
Which is your expertise.
Yes, it is.
So, wonderful. Great. Dr. Kreitz, what have you been working on lately?
Yeah, thanks. So yes, I'm Abby Kreitz, and I'm a professor at the University of Toronto in the Dunlap Institute in the Department of Astronomy and Astrophysics. And basically, for my job, I build telescope instruments. So I build cameras that are installed on telescopes and used to observe things in the early universe. So one of the things that we're doing right now is we're building a camera that can look at some of the first galaxies that were formed in our universe. And because they're so far away, they're very faint, and the light is actually a different wavelength from the light that our eyes and typical cameras measure. So we build these really specialized cameras to actually observe these galaxies and observe other really faint signals from just after the Big Bang. So that's what I work on. And, usually I'm in a lab, actually kind of using screwdrivers and drills and, actually assembling these instruments. But right now, since we've been working from home, I actually have worked with a lot of students to actually do computer simulations of our instruments. So basically, we design the instrument with our computer, and then we can actually do simulations of how they will react to being cooled, to different, physical things that can happen to the instruments. So we're kind of doing physics of our actual instruments inside of our computer in preparation for when we go back to the lab and can assemble them and use them in person.
Amazing. Very productive. Thank you. Dr. Hlashek.
Hi, everyone. I have been having a super exciting few weeks. So just like Abby, I work on telescopes, some of which use measure light that isn't visible to our eyes. I actually do some of the analysis, like statistics and the processing of data from a telescope in the Atacama Desert in northern Chile that's measuring light from the Big Bang. And this telescope's been operational for a decade, and we've been scanning the sky, and we just have a bunch more data that is ready for analysis. And what I'm doing is I'm using that data to understand what were the very first moments of the universe like, and how did all of the stuff start in the universe. So just these density fluctuations in the universe, and we're trying to sort of backwards estimate that from the light that we see on the sky today. So it's been super fun. We're trying to get our results out, so it's been crunch time, but I've really been enjoying it. I think you're on mute, Mike.
Sorry, I was muted. Yes, thank you very much, Dr. Hlashek. So I'm now going to ask everyone a surprise question, which is, did you see Comet Neowise? How many of you went out and looked for it? Any anecdotes about what you saw?
I did get to see it. Not very well, though. I saw it on, I think it was either Thursday or Friday night. I went out to Scarborough and the skies were really dark, but not dark enough to be able to see it with my naked eye. But I had some binoculars and I was able to just see this faint little trail in my binoculars, but that was about as good a view as I got, unfortunately.
I was sadly not able to go far enough out of town to see it. But the cool thing about having so many astronomer and astronomy interested friends on Twitter and Instagram and Facebook is that all over the world is that I got to see it NeoWise over a bunch of different settings with my friends' amazing astrophotography. So it was a close second.
Very nice. Abby, did you see it?
No, I didn't get to see it. I'm also kind of in the middle of Toronto and also facing the wrong way for anywhere I can get high up in my apartment. I do have a balcony, but it's facing the wrong way. So I wasn't able to see it, but I did enjoy everyone's pictures of it.
Nice. Okay. So I feel like I'm the only one who had more ideal observing conditions. I don't live in downtown Toronto, so I was able to see it even with the naked eye, which was really, really delightful. Very, very nice experience. Okay, so let's get to some questions from the audience. We have piles and piles of them. I'm going to start with the ones that are being asked live right now on YouTube. And then if those slow down, we'll go back to some of the ones from social media. So the rules are basically any of you can jump in on any question that you feel you can help with. Sometimes I'll try and pitch them to a person who I think may be able to answer them best, but feel free to jump in. So the very first question comes from Jason, and he says, what constellations or stellar phenomena or planets, moons, whatever, are your favorite to look at? What do you like looking at? Renee.
So I'm super excited by this because, and I'm sorry, folks, you can't see this from the Northern Hemisphere. I'm from South Africa, and so I'm super biased because we have the most amazing sky. But one of my favorite things to look at, it's not particularly cosmological, which is what I care about, but it's called the Jewel Box Nebula. And it's the Jewel Box cluster. And it's basically a cluster of stars, but you can see in pictures just the different colors of the stars. And that's why it's called the Jewel Box. And I just love it because it's not only beautiful, but it also tells us something about the evolution of different stars and how massive they are and how hot they are, which is really fun.
Very nice. Anyone else want to jump in on that? What do you like to look at?
Okay, this is also kind of a hard one because you can't see these things all the time, but the best thing I think that I saw in the sky, besides a full eclipse, was the transit of Venus. So this is probably like 10 years ago now, a bit more, maybe like 8. Anyways, so I think that the things that I like to look at in the sky are super different from the things that I study. And I think I like that because it was so visceral, like something you can see with your own eyes, just with, solar protective glasses on. But I really think that it's kind of hard to visualize the things that I do for science, like the things that I see with the telescopes that we build. So for me, it's just really cool to see something, with your own eye and kind of feel that attachment to the universe that you don't always get when you're working on your instruments.
Wonderful. Ilana?
Well, the things that I like to look at in the sky are actually pretty easy to see. I love looking at a moon or the moon through a telescope, like just looking at a moon that's just before the first quarter, for example, and you can see all the nice craters being highlighted by the shadow and the sun. I just think that that's really pretty. And I like looking at Jupiter and Saturn, and I like looking at, there's a binary star system called Albireo that when you look at it up close, one of them is a reddish star and the other one's a bluish star, and you can really distinctly see the different colors of those stars in the telescope. So I like to look at things that are actually pretty easy to pick out with a telescope.
Very nice. Okay, so there's another question here. Maybe we can answer this one quickly because we discussed it just before we started. What type of telescope do you use to stargaze? And I think we can allow this to wander into our research if we like. But you can answer the question about do you have one at home as
well? I don't have a telescope at home, unfortunately, but I've been thinking about getting one. And before the pandemic started, I would often go up onto the roof of the McLennan Physical Labs building and look through the telescopes we have there. So and they're a 16-inch reflector telescope and an 8-inch refractor telescope. And they're both very cool looking.
So yeah, I have a really small refractor telescope that is kind of like you can just hold it up. So it's very close to binoculars, but it just magnifies things a bit on the sky, so lets you see things. But you don't have to worry about kind of pointing the telescope that well, as long as you can see the object with your eye to begin with. So that's what I use at home. And then for work, so I actually build instruments that use cryogenic detectors. So they are these detectors that are cooled down to 1/4 degree above absolute zero, and they actually detect very, very faint low energy photons from things like Renee mentioned, so like the cosmic microwave background, and also signals from really early galaxies. So they work pretty differently from the way cameras and the optical work and the way our eyes work, but they do the same thing. They pick up signals from those galaxies and let us read them out. So we read them out with a computer and make maps with our computers.
Wonderful. Renee, do you want to chime in?
Yeah, I just, as Abby said, I use similar telescopes to the ones that she uses. And I think it's kind of cool to think that we think of our eye as taking pictures and making sense that way. But a lot of the stuff that I look at on the sky, if you just were to see it, it wouldn't look like a pretty picture, or it does to me. But it really relies on the fact that we build big telescopes, which are like light buckets, and then we use complicated software and big cameras to actually record that into signals. So if you love computers, actually, then astronomy is a really good job for you, because there's a lot of cool processing and like cool techniques that we use to turn those images into something useful.
Okay. So sorry, I'm having slight internet problems. So if I wind up talking over you, my apologies. So on riffing off what Renee was just saying, we have a bunch of questions from Julia Ma, and they're all sort of about, becoming an astronomer. We actually have somebody else asking similar questions. So one of Julia's questions is, how can a young person do what you do? What things can they read or do or learn? And she also asked, what kind of math do you use on a regular basis? So anyone can jump in on this, I guess.
I can jump in on the second part, the kind of math that we use. So what I love about the universe is that a lot of the equations that govern the universe are actually pretty simple, which sounds like the opposite to what you might expect. But we use some very simple equations, like the equations that govern gravity are Newton's laws, and those are actually really simple equations that you will have started to learn in high school and early college. And then a lot of the math that we use is general relativity. So if you've heard of Einstein, he and others contributed to this mathematics. But the cool thing about it is that once we kind of know how the universe kicked off, we can largely predict the future of the universe if we know what the universe contains. And so the calculations themselves are simple to write down. They're not always simple to do, but they're simple at least to write down. And then we have a lot of power in the future. So there's a lot of fun math that we use.
I could add something, or? So, I mean, one of the things that I love about astronomy and doing astronomy is that there are so many different jobs within astronomy. Like even with the three of us here and plus Mike 4, there's like, we all do very, very different things in astronomy. And we're kind of all, kind of asking the same questions of like, what's in our universe? How does it work? That kind of stuff. Like we're teaching and learning about our universe, but we all do it very different ways. And I really like that. Like so I said I use screwdrivers, like I have a very hands-on job most of the time. I'm actually like building things, putting them together. There's a lot of Python programming in my job. People program using other languages. You might do like basic math calculations for a lot of your job in different areas of astronomy. So I don't know. I feel like there's a lot of places you could enter astronomy and you could have a ton of very different interests. Like there's a huge spectrum of interests that allow you to be an astronomer. And, you might love being at your computer doing programming, or you might love, building things, or you might love making these 3D models of the instruments like I make, and kind of visualizing them in your computer. I don't know. I love that.
Yeah, I think that the path that one takes to become an astronomer can be vastly different, because my path was very straightforward. I just studied math and physics in school, did an undergraduate degree in physics, did a PhD in astrophysics, and then, went from there. But, there are many people who come at it from different angles, from like engineering, from mathematics, from some people just were studying English and they're like, hey, but astronomy is cool, let's do this instead. And so it's as long as you have an interest, having like that basis in math and physics is useful, but it's not necessary. You can always come at it from a different angle too, if you're really into building stuff or figuring out how to code things to explain, to model the universe or anything like that.
Oh, sorry, I was muted again. We have a bunch of questions about gravity, and I really don't know who to direct these to. Maybe Alana to start. So one of the first ones is, how does gravity work? Why should masses attract each other? Does anyone actually know?
I think the answer is we don't know why gravity works. We know that it does. We have very good models for explaining how it works. To a very good approximation, Newton's universal law of gravitation does a great job of explaining why masses are attracted to other masses. And general relativity does an even better job of that, of explaining how mass affects the curvature of space-time. But I don't think we know exactly why mass attracts other mass. And I think you'd have to get into like crazy stuff that I don't actually know. So maybe either Renee or Abby have more to add to that.
I mean, I think one of the cool things is that when we start off, when we're younger, we think about someone had to do something, right? So you throw a ball or the earth is pulling on the ball. Like you think of the earth having I don't know, like when you make an analogy, you think of it having an action, you think of it having like some kind of will to do something. It's very easy for us to think that way because that's how we feel on Earth. But to sort of understand the gravitational field, and as Alana talked about, the link between the stuff in the universe and the curvature of the universe, and the curvature then talks about how things move, and that movement is sort of what we perceive as orbits and gravitational attraction. Once you link those things together, you start to have a much more holistic picture of the universe in the sense that it is a space-time and it has a relationship between gravity and the stuff in the universe. But then you have to think of the universe as a whole and not necessarily separating into these little parts all over. But that's what makes it super exciting. The more we learn, the more we build a picture of the laws and the rules of physics that govern both the small scales and the very largest scales in the universe. And that's one of the reasons why I study cosmology, actually.
Anyone else want to jump in on that one? I have another gravity question then, related. So how far away are we from being able to detect gravitational waves from just after the Big Bang directly with a gravitational wave detector? Or I suppose any other method if you have another method.
I should be able to answer that. It's been a while since I've thought about gravitational waves. I believe that it depends highly on what those gravitational waves look like. So currently, if they're within a certain frequency range, there is a possibility that with our current detectors, we might be able to see them. But if they're at a much smaller frequency, then we'd have to wait until we have detectors in space to be able to detect those. And that's probably at least a decade off. But yeah, that's a good question.
Renee, were you going to jump in on that one?
Yeah, I was just going to say, I think it's really great that you raised the point of detectors or other methods, because the whole world is super excited, as it should be, by the direct detection of gravitational waves from, the coalescing of massive objects, so, binary black holes and black hole neutral stars. And those are big, exciting events in the universe that are, as they spiral into one another, they're really distorting space-time around them. And so these ripples then can be picked up by individual detectors. But the kinds of gravitational waves that we think will come from the early universe are they're a much different frequency, and they're much kind of lower in amplitude. You can kind of think of, they would be more like distortions that are much smaller, and so they're harder to detect. But what we can do is we can detect them indirectly through how they change the pattern of light from the Big Bang, right? So this cosmic microwave background that both Abby and I study, that pattern on the sky will be distorted if there were gravitational waves around, if there were these tensor modes, if we're getting super technical, but let's not. And so we can detect indirectly that there were gravitational waves from the early universe by how it changes this pattern on the sky. And both are important. And the second one, the thing that I work on, we're making huge advances in our detector technology. And so my fingers are crossed that we'll be able to detect, if they exist, gravitational waves from inflation in the next 5 to 10 years.
I was just waiting to see if Abby was going to chime in. That's okay. So lots of questions here. That's really wonderful. We'll have some more about gravity, but I think I'll leave a few of those for a little later on. We have a really interesting kind of series of questions here from Jenna Gu, who says that she's an incoming U of T, University of Toronto student who's interested in pursuing physics research. And she has a kind of series of questions that ask about attending seminars and talks. And if I try and sort of summarize them for you, she's saying, you know, she realizes that after trying to attend some seminars or talks, the content isn't very systematic. It's all over the place. She's worried maybe a little bit about not being able to understand seminars or talks, and what do you do during a seminar or a talk. So I think this is, you know, this may seem like a question that's kind of particular to U of T or to academia, but I think it also touches on how we communicate our ideas in science and how we share our knowledge. So I don't know if anyone wants to jump in and give Jenna some advice about what to do during seminars and how to approach them.
I could give some thoughts, and Renee also should, because one thing I will say is that Renee gave a talk to us about how you listen to talks and how you learn from talks. So I'm sure she has some great advice too. But yeah, I think maybe that's just to acknowledge that we're all kind of having that same question, like throughout our careers, that yeah, depending on the subject and how close it is to your field or how far away or how new you are to the field, you know, there can be various different experiences during talks. And, you know, one of the things that I like to do is kind of give myself a break just up front, that like I'm learning something new and that's what I'm there for. And, you know, I might not know everything or, you know, even anything in the talk to begin with. And kind of one of the things that I like to do is bring a notebook with me so that I can write down things and not bring any of my electronics. Like I don't bring my phone or my computer, or I try not to be on any of those things because I think that really distracts me. But if I bring a notebook and I write down the things that I find interesting, and I think this was also one of Renee's suggestions that, from her talk to us, but I often will get the information of the speaker and like ask them questions via email afterwards, if it's something that I'm really interested in. And I don't know, those are just my early tips. We can discuss more because I think this is a really cool question.
Yeah, I think it's a great question. And I also, if I can add, I have like a little bit of an analogy just because this is a general audience that I think is super useful in specific contexts as well. So I don't know if anyone has watched the movie Inception. So it's if you haven't, it's a fun movie to watch and it's quite complicated and there's a lot of stuff that happens and the end is nobody really, you know, you have to really pay attention. I don't know if you've ever watched that kind of movie with someone who interrupts and asks questions a lot during the movie. Like they can be like, okay, but why is this person doing this? And they can often distract you. And sometimes I feel like when we want to pay attention in a talk, we think we have to understand every little thing. But that's really like that irritating person being like, wait, why is she wearing red now? And what is this guy's name? And have we met him before? So I often try and calm that side of myself. And as I'm taking notes, exactly as Abby said, I just try to write down like important stuff that might be important later. So if you think about Inception, it's like that spinny top thing, that's going to come up again. So I just write spinny top ? And then as I go through the talk, I like allow myself to add to a little note that I took before and to build up. And if there's a question that comes up that seems to be pretty critical and important, then I write that down. And at the end, I look through all my questions and I think, which question should I ask the speaker? Like which one is going to really help me unlock the whole movie? And if you start actually just keeping that in your head, whenever you go to a talk, think of it as like Inception. You just want to tell your friend what the movie's about later. You don't have to know every little detail. And you just want enough information that you can think about it again when you go home. Because if you write down just enough details, you can kind of keep processing it. And if you do it like that, it becomes much less stressful because you're just imagining, all the Inception characters doing their fun stuff. But also it takes the pressure off understanding every word. Because if you understand every word, you often miss the whole point of the talk. So.
Yeah. I think that's great advice. And I would say to Jenna, first of all, I didn't say it before, congratulations on being accepted to university and coming to U of T and joining us. If that wasn't enough to answer your question, I'm going to speak on behalf of everyone and say, I bet that we would probably all be willing to chat with you at some point if you wanted to learn more about how to get the most out of your time at university and out of your path toward potentially becoming a physicist or an astronomer or whatever you might like to become. Okay, so Bruce asks, extreme solar activity can create havoc on our communications and electronics. How are we getting ready for the peak of the solar activity cycle? This is a tricky one for astronomers. This is almost an engineering question.
I don't know that we are getting ready for that, are we?
I think we as astronomers
are not.
We're getting ready to tell you when it's going to happen. And
so actually, weirdly enough, I studied when I was doing my physics undergraduate degree. South Africa is really interested in ionospheric physics. So the ionosphere is, the kind of very top of the atmosphere, and it's the part that has a lot of the charged particles in it. And we have a lot of lightning in South Africa. We don't have any of the aurora typically, but we have a lot of lightning. And so I did a little mini half course on ionospheric physics, and we studied the McGill catastrophe, that McGill's grid got overloaded, I think in the 90s because of a solar storm. And so I think at the time, at least, folks were talking about how one of the ways to get ready for a solar storm is to just make sure that your power grids are not all linked together, so that if you have to dump power, that you're able to distribute in the network pretty successfully. But the other thing, as Mike actually said, is early warning, right? The reason why we have the solar observatories, so the telescopes that look directly at the sun and block out the main part of the sun and can really look at the corona and can look at the ejections that are coming off the sun, is partly because the warning may be only minutes or hours, but that will be enough to say, let me shut down a grid for a little bit of time so that everything is not blown and that you don't necessarily get the full brunt of the storm.
Okay, super. So Ben asks a fun question. What would be the best place to get astronomy news for someone who's less scientifically literate? What are your favorite sources for, popular science kinds of stuff?
Mine is Mike Reed.
All the other Cosmos from Your Couch videos. That's a good start.
I find a good source is Sky News. That's a good one. Sky and Telescope, if that's still a thing. There's also the Nature, popular science, not the scientific papers, is a good place. Same with science. There's a few reputable news sources that are pretty good for astronomy news that hasn't been twisted around to seem more exciting than it actually is. That's something you have to watch out for.
One of my favorites is from a long time ago. I don't know when this started, but it's called APOD. So it's Astronomy Picture of the Day. So it's basically one picture and then the explanation. And I love those. And yeah.
If you're interested in video content, a really good YouTube channel for astronomy stuff is SciShow Space, SCISHOW Space. It's very, they release a lot of videos and they're very topical. So if you like to hear about, what's the latest thing that happened, they often have lots of good content. Okay, so let's go to some of the questions we received via social media. So this is a question from someone suspiciously with the same last name as Dr. Kreitz, who asks, what is the most surprising or exciting discovery you've made?
I'll take that one, I guess. So, I mean, I really like this question because I think it lets us kind of break down some misconceptions that we might have in the world about what our jobs are like as astronomers. And I think one of those things is that we make discoveries every day or even every year. And also that some of the other things that are often thought about when you're talking about discovery is that one person makes a discovery. But I think that it's really like one of the things that I love the most about this field is that we actually work together on huge teams. When we discover something, it's because, maybe 20 or 50 people even spent 5 years building an instrument to make this measurement. And that's what I do every day. I work on big teams of people to build cameras. And like, Renee mentioned, like these super sensitive detectors that we're making to try to measure those B modes. So if we measure those 5 or 10 years from now, that'll be decades to like many decades of work of, hundreds of people in our field to kind of make this one thing that tells us something like quintessential about how the universe began. And I mean, I think I was very lucky during my PhD. We made a measurement that I considered very exciting, and it was also team-based, and a bunch of quite a few teams, well, a handful of teams made the same measurement around the same time. But that was actually, so Renee mentioned the cosmic microwave background. So this is this light that was emitted just after the Big Bang. And one of the ways I like to think of it is kind of like a baby picture of the universe. So it tells you like what the universe was like when it first began. But the cool thing about this light is that it's been there, for almost the entire history of the universe. And it actually doesn't just tell us things about the beginning. It tells us so much physics about our universe as it's evolved. And one of the things that you can do is you can actually, so there's that distortion Renee measured. There's another distortion of that light that actually comes because there's big galaxies and clusters of galaxies between us and when that light was emitted. And that actually distorts the CMB also. So one of the cool measurements that we made when I was in graduate school is we actually measured this distortion in the CMB. It's a different one than the one from the very, very early universe. But it's just an example of how this light that we measure and have been measuring for decades just has an immense amount of physics of our universe in it. And we can just kind of make new measurements of it. We can make these cameras more and more sensitive so that we can see the tiny, tiny fluctuations and distortions in it. And we're just constantly improving those cameras as teams to actually do this. And I don't know, I'm just like immensely proud of creating that with people and of making that measurement with like these amazing, amazing people. I think that's like the best thing about it.
I think it's so cool. I was about to say the exact same measurement, like that, that our different teams made. That was just, yeah so cool.
Yeah.
Amazing.
The other thing I don't know if Ilana wants to chime in too, but I was also a little bit emotional, I guess, because I just moved to Canada. But in early 2016, when LIGO made the announcement of the detection of gravitational waves, I was getting my furniture from the border from Mississauga. And I actually had to pull over the road and I just cried, not because I'm part of the telescope or the collaboration at all, or because I was worried that Einstein's theory of general relativity was not going to be proved correct, because I'm not worried about that at all. But I really cried because I know, as someone who has colleagues like Abby who work on instrumentation, I know that the building LIGO took decades of people pushing and fighting to make the most incredibly fine measurements. And I think one of the things about science is this huge stamina that as a group of people need. Individual people have their own research, but as a group, we're making these slow, hard tasks, and we're like spinning glass into these tiny threads that are used to hold up incredibly massive blocks that will wobble by a tiny fraction of a human hair, and then we'll be able to detect gravitational waves. Like the scale of all of it just blew my mind, and I had to pull over the car and just cry. It was great. So.
Yeah, that was definitely an amazing moment. I studied gravitational waves when I was doing my PhD, and the specific project I was doing, I had to measure how good models had to be in order to actually know something significant about these gravitational waves that we would eventually detect. And I was like, I don't know, it's going to be so hard. I don't know if we'll ever be able to do it. And then I graduated, and then I guess 2 years later, the actual first detection was made. And I just started a new job at that time. And I saw the announcement on my phone, and I was like, and I told my boss, I turned around to her, I'm like, I'm sorry, I have to keep looking at millions of press releases right now. I can't work right now because I'm too excited. And she's like, I get it. But yeah, it was pretty crazy. And I only had like a very small part to do with that discovery at all. Like I would say that maybe I contributed something that helped somewhere along the way. But like, yeah, just knowing that it was like, the discovery of the century. say.
Powerful moment. Okay, so now a quick and easy question from Endevi. And Endevi asks, are M dwarfs the same as red dwarfs? Who wants to jump in?
Yes. An M dwarf is a classification we use for a smaller type of star, which is called a red dwarf. It's a star that is much less massive than the sun, and so it is fusing hydrogen at its core at a much lower rate, and so is not as hot on its surface, and things that are cooler tend to be redder, and hence M dwarfs. So yes, or hence red dwarfs. So an M dwarf is the same thing as a red dwarf, and it's just our classification for it.
Okay, so now we go from the very easy to the much less easy, perhaps for our two cosmologists. So Isabella asks, will there ever be an end to the universe?
I'll take a stab at it. So yeah, I love these questions. So I think that one of the things that we know about the universe right now is kind of like its content. So how much of it is made of different things. So you might have heard of some of them, like dark energy, dark matter, baryonic matter, which is basically all of the stuff that we can see that interacts with electromagnetic radiation. So we kind of know about the content of the universe, and we know that the universe, because of this dark energy, is actually accelerating in this expansion. But we really don't, we kind of have like a snapshot of that. So I think we really don't know what the universe will do. You know, we could imagine that it would continue to accelerate in this expansion as it is. But one of the things that a lot of cosmologists are interested in to kind of get handles on what will happen is kind of how do these different portions of the universe evolve over what we call like cosmic time, so like the age of the universe and how it's been evolving. So if we can figure that out a little bit more, we can start to get like some ideas of maybe trends that are happening. But I think that the short answer is like we really don't know. And that's kind of, I mean, one of the exciting things is we don't know a lot.
Renee, do you have anything to add?
I guess the only thing is that what I love about the universe is that we're not going to matter very much. So Abby was talking about the different stuff that is in the universe, and we have 5% of stuff that we kind of know and love: stars, gas, you and me, planets. But this dark energy in the universe is has this weird property that as the volume of space gets bigger, it becomes kind of more, there becomes more and more of it because its density remains constant, which means that in the future, if we counted up all the stuff in the universe, we would make up a much smaller and smaller percentage going forward. And so what I love is no matter how the universe ends, if it does at all, it will be almost vanishingly empty of stuff we know, which means the whole future of the universe is going to be filled with stuff that we don't really understand yet. And yet we happen to live at this incredible time. Cosmologists actually call this the coincidence principle. Why do we live now when there's a little bit of the other stuff that we can see it and can understand it and start to think about it, but there's also enough of us, there's enough galaxies, there's enough stars that we can also enjoy them. Because if we lived very far in the future, we would look up at the sky and it would be dark and we wouldn't see stars and we wouldn't see galaxies and we would think we were alone. So we live at this super fun, important time, cosmologically speaking. I don't mean like Tuesday, but we live at this important time where we can see all of the other stars before we become insignificant.
Terrifying thought, terrifying. So I think we'll come right back down to Earth for a minute so we don't spook too many people out with our cosmological speculations. We have a pair of questions that are related here. I'm going to take a stab at helping with these because it's sort of my job at U of T to answer these questions, and then I'll let the others chime in. So Reed Oda is asking, what advice do you have for people interested in physics but who had a bad experience in physics class? And Isabella says, if you're a high schooler interested in a career in astronomy, do you need to take chemistry, biology, and physics, or just physics? And do you need to learn programming? So let me break that down for you really quickly. If you had a bad experience in physics class, first of all, we're sorry. We apologize. Lots of people have bad experience in physics classes. And, you know, honestly, part of the reason for that is just that when you're getting going in physics, there's a lot of, not always very fun stuff to learn at the beginning. There's some pretty boring kind of grunt work to do. And if you don't have absolutely the right teacher, it may not be super fun. And that was a lot of people's experience. That was definitely my experience. I did not love physics in high school. But I knew that there was something better coming, right? I knew that this was going to be the ticket to a really big journey that was going to last a lifetime, and it was going to be amazing if I just stuck through it. So if you had a bad physics experience, absolutely do not let that taint your impression of becoming a physicist or an astronomer. It gets really, really good, especially around the second year of university. In terms of what courses should you take? Yes, you should take chemistry, biology, and physics if you possibly can. You won't run into biology day to day in most parts of astronomy, but you will run into chemistry and physics, and you might run into biology if you decide to become an astrobiologist or something like that. As for, do you need to learn programming? Yes, you need to learn programming. This is something we run into all the time with undergraduate students at university who have never programmed. And it's sort of just assumed these days that if you have a career in science at some point, you will have picked up programming, but it often isn't taught. So if you have an opportunity to learn it, definitely take that if you can. Does anyone else want to add to?
And also, I think programming is sometimes seen as scary, and people don't want to do it. Programming, I initially thought I never wanted to do anything to do with programming when I started college, and now I love it. It's so great because you get a big computer to do the thing you want to do fast. It's great.
So I seem to have scared Isabella there. She says now she's scared for her physics class. Don't worry, your physics class will be fine. It just may not be, fireworks and explosions all the time the way you might hope it will be.
I also, sorry, didn't mean to.
No. Yeah.
Oh, I guess I was going to say that I think part of this goes back a little bit to my thing. There's a very diverse range of things you can do as an astronomer and physicist. And so for me, some of the, I also had not the best time in the undergraduate physics classes. But I think part of our job maybe as teachers is also A, to make that a good experience, but B, to make that as close to as possible to what your experience in this field might be like, so that you can get a taste of that and know that that's what's to come. Because for me, I was very, very lucky that I had an experience with research as an undergraduate. So I could kind of say, it's going to be okay, you're going to be doing this all the time soon. But I think that part of our job as teachers, I hope, I'm very new, so I'll learn if this is true, but part of our job is to kind of teach in a way that connects it to all of the different stuff that all of us on the screen do earlier than, having to just struggle through that till you get to graduate school. And also programming, I am the same as Renee. I tried to learn to program in college, but it didn't work. And when I started learning it for my job in graduate school, I started to understand that it was a tool, and it made more sense to me, I think, then. So I don't know. I mean, I also hope that part of our job is to reach all of you and help scaffold that for you, because we've gotten here and we want to help.
It's the best job in the world. I have the best job in the world, so.
Great. Okay, so another science question. Ayush asks, it's a long one, so just prepare. Earth-like features are a prerequisite for life to evolve in any part of our universe, or so it seems. And it seems inevitable considering the formation of life on our planet that, life should evolve along those lines. But do you think there might be life on planets without Earth-like features? So do you think there could be life on some planet that's totally unlike Earth?
So I think one of I'm not an astrobiologist, and I don't necessarily study planet formation or formation of life on Earth. But I think one of the issues is really the reason why we look for Earth-like planets is not because we think life can only evolve on Earth-like planets. It's this sort of lamppost problem, right? We look under the lamppost. If we drop our keys, we look under the light because there's light there. And so we look for life on Earth-like planets because we know it's happened once before. And yet a lot of people in this growing field that Mike mentioned of astrobiology and astrochemistry, a lot of people are looking on Earth at very places on Earth that are very hostile to life. So for example, you can go to very acidic places or deep under the ocean where there's a lot of pressure, where the concentrations of salt are really incredible or whatever, and you can find that there are these life forms, these organisms that live there. And so as we understand more about extreme conditions, even on Earth, we can think, okay, what would life be like if the temperature was very cold or very hot, or if there were different chemicals? So I don't think we actually think only life on Earth is possible. It's the safest place to look first for my keys that I dropped on the ground.
That's a great answer. Great, I agree. Okay, so interesting little kind of controversial political question here from Nathan Donnellan. What are your thoughts on Starlink? This is Elon Musk's satellite constellation. Is it the end of ground-based telescopes, or is it an overblown crisis, or something in between?
Do you mind if I start this?
Of course.
Okay, so I'm one of the other, so I mentioned that one of my telescopes that I work on measures light from the Big Bang, but another telescope that I'm involved in is also being built in Chile, but we are looking at optical light. And this is called the Rubin Observatory, named after Vera Rubin. And it's a project that has been under construction, under planning and construction for decades, and is going to have first light in the next few years, 1 to 2 years. And Starlink is really going to be terrible for LSST. We already see trails of the Starlink fleet in other ground-based telescopes. And yes, it's not going to mess up every one of our images or for all of the night, but this telescope that we're building is costing, $1 billion. And there are hundreds and thousands of people like me working on making sure that the data are correct. So even if we have to throw away 10% of our data because there are these streaks in that make the map or the picture just unusable, that's a huge financial and personal loss to science. Now, of course, everyone wants Wi-Fi all over the place. And so I understand there's been a lot of pushback on the internet. Scientists need to stop complaining. But, my goal, the reason why I get out of bed in the morning is to understand the way the universe is put together. And I'm giving my whole energy to do that. And we're putting so much effort in that to just lose that without even asking if it's something that we need or if there's another way to do it, I think is a huge travesty.
Yeah, no, I agree. This is a question we get asked a lot. What do we think about Starlink? And I think it depends a lot on the kind of science you do and whether or not Starlink satellites pose a threat to that science. But, one of the things that I think bothers astronomers a lot, you may know that we are always talking about light pollution, right? And the loss of access to the night sky because of all the excess light generated by human civilization. To think about exporting that off planet and starting to sort of pollute the near Earth environment with stray light, it's one of those situations that's kind of hard to come back from. Once you've obliterated the ability to make these observations from Earth, it'll be very hard to return to being able to do that again. So I think what distresses a lot of people is just that there could have been a more consultative approach to this that would have made it have less impact. Maybe there still could be. Okay, so more questions here, lots more questions coming. So another kind of political one. It's everyone else's kind of other favorite big astronomy anxiety, not Starlink, but JWST, the James Webb Space Telescope. So this question comes from Eli, who asks, will the James Webb Space Telescope be finished by 2021? And will it be finished effectively, given all of the things that are going on in the US right now and the world?
I can say something and redirect because I am super excited for the science that telescope will do, because it's really related to what I do. So I mentioned at the very beginning that I am really interested in some of the first galaxies that were formed in the universe, and they're really hard to measure. So we can get with the Hubble Space Telescope, we've measured already like a handful of these galaxies, but with James Webb, we'll be able to measure more of them. So we'll be able to see these really faint galaxies at like 1 billion years after the Big Bang, when the universe is like 14 billion years old. So that's pretty far back. And one of the things that is difficult about these is that they're really hard to measure because they're super faint. And also the light from those galaxies gets shifted as the universe expands into like lower wavelengths, and it's harder to measure with telescopes that are designed to see light that our eyes can see. So yeah, so I mean, I'm excited. So, you know, you want to put a telescope in space for that, or you want to do it some other way. So I'm really excited about James Webb, but sometimes when you build these really, really huge projects, it takes a really long time. It takes longer than you would expect. So one of the things that I'm excited about as an instruments person is kind of getting at those galaxies other ways. So we're building an instrument that can see that kind of signal from those galaxies, even the super faint ones, kind of all integrated. And one of the things that I think is really fun about kind of modern astronomy is we're trying to build these instruments really quickly. So, you know, instead of, you know, taking many, many years, we're kind of thinking of other ways to study early galaxies that you can do in maybe like 2 to 5 years, or, you know, max 10 years in terms of measuring these things. But that doesn't really answer your question, and I totally admit that. But I'm also excited for learning more about those galaxies, and hopefully we will. But like, as scientists, I think Renee said this, we're very like, we have a lot of perseverance, or, you know, collectively we're just like, let's do this. And I think that one of the ways we're doing that is to like try to get at these signals other ways. And there's tons of other stuff with James Webb other than like early galaxies that I'm interested in. But, you know, we're all trying to discover more about the universe.
Ilana?
Oh, yeah. I mean, it might not launch next year, but I'm confident that it will eventually launch, because if history has taught me anything about astronomical instruments and their launch schedules, it's that, you know, it's like, oh my God, it's delayed another year. Oh, when is it ever going to happen? And then it does eventually happen, and then we get awesome data from it, and everything is amazing. So I think that might not be next year, but hopefully eventually, and definitely eventually. with optimism.
I love your optimism. Yeah, I
Yeah.
think that's, yeah, it's a common thing for things to get delayed and then all of a sudden they're there.
Yeah.
Even our stuff that's quicker. Like,
yeah,
it always takes longer than you expect.
I think of LIGO, which the Laser Interferometry Gravitational Wave Observatory that made the first detection of gravitational waves. That took, well, they started designing it in the 70s, and it only made its first detection in 2015. So that was a bit of a long haul. And during my career as a grad student, I'm like, this has been going on forever. It might go on forever still. Like, it, you know, like when they first turned it on, it didn't have nearly the sensitivity they'd hoped. And then, you know, they worked on it, but then it eventually made the most incredible discovery. So yeah, I'm confident that these things will eventually be achieved.
Okay, so we have some fantastic cosmology questions now. I'm going to try and see if we can get through a few of them before we wrap up. So Chitana asks, why can't our telescopes see beyond the time when there was a Big Bang? Do we call that the edge of our universe? Renee.
I'm super excited. So we can see as far back, we can see to the point where the universe really looked like, kind of like the inside of the sun. So we think of the 3 phases of matter as solid, liquid, gas, but really there's solid, liquid, gas, and plasma. So when you make things very, very, very hot, the atoms are kind of split apart and you get electrons and nuclei. And so when the universe was super, super, super hot, you had these electrons and nuclei just around, much like was what's happening in the sun. But the key thing is that light bounces off electrons. The same reason why you have kind of neon gas, so light bounces off electrons, light, those kinds of interactions make light opaque inside the sun, and the same thing happens in the early universe. So we can only see up until that point, which is about 400,000 years after the Big Bang. So as the universe cools, it's very, 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 very hot, and then when it gets to 400,000 years old, roughly, it's cool enough that the electrons and the nuclei can form stable atoms, and then the light stops bouncing around. And so that's when that light can now kind of travel towards our eyes. In fact, it's all around us, but that's why we can't see further than that. So a lot of the work that we do is kind of trying to take the light that we see and figure out what was happening before, even though we won't ever be able to see that with light itself. Maybe with gravitational wave impacts, but not light itself.
What if I build a really big telescope?
Nope.
Then can I see beyond the Big Bang? No.
Nope. Sorry.
Okay. So another kind of related question is, what triggered the Big Bang? What broke the balance? This is from Lin Yang, who said, part of the question is, was the universe isotropic before the Big Bang? And how could the balance have been broken? You know, was there something that came from outside the universe to cause the Big Bang? How did this happen?
I'm happy to go again, but I don't want to steal the, okay. And then I'll give the next one. I won't answer it all. Okay, so great questions. I'm going to answer a couple of them all together. So first of all, we think the universe actually, on the largest scales, kind of is isotropic, which seems strange because it doesn't.
Can you tell us what isotropic means?
Yeah, so isotropic means if you look in every direction, the universe looks the same. So there's no special point in the universe. Now, of course, that feels really weird because the special point is obviously my apartment, I'm sitting in it, or the solar system, or the sun. But if you go on the biggest scales of the universe, if you really zoom out, there's no special place in the universe. It looks the same in every direction. And so we actually think the universe is pretty isotropic. There are very small anisotropies, and those anisotropies or not isotropy points are actually what form everything else later. And they sort of become more and more not isotropic with time. And to the first part of the question, it's always difficult to not picture the universe and the Big Bang as an explosion that happens in a box, right? In a bigger universe, there's a little explosion. But really, the Big Bang is the universe, right? That the universe, there wasn't something outside that like ignited the Big Bang. We think of the universe as it happened, the whole Big Bang happened everywhere in the universe at the same time. Now, that didn't answer your question. Your question was, why did the Big Bang start? And that is a very valid question that many of my colleagues spend all their time thinking about. You can either say, well, that's just our equations. That's when we define, t equals 0, time equals 0. Some people say that's not satisfying. Some of my colleagues at the Perimeter Institute, including Neil Turok, say, oh, actually, if we had a universe that was sort of bouncing, then maybe we would have these Big Bangs and they would repeat. And the truth is we spend a lot of our time trying to figure it out in terms of equations and trying to understand the implications of those equations on this light that Abby and I measure.
Okay, anyone else? No? Okay, so jumping way down back towards the Earth now into the solar system, what are your thoughts on the recent theory that Planet 9 could potentially be a small black hole? Could there be a black hole in our solar system, to put that another way?
I haven't heard about that theory. It seems a little bit out there, if you'll forgive the pun. I think that likely Planet 9 is not a very small black hole because it would have to be, well, okay, so black holes are points of infinite density where everything except for gravity or gravity has taken over from any force that could push outward, so it's collapsed in on itself completely. And so the larger an object is that became that black hole, the sort of bigger that black hole would be. And so to have a black hole that is orbiting around the sun, the original mass of that object would have had to have been about the size of a planet in our solar system. And we don't know of any way that you could actually form black holes from that. On top of that, there is this idea that smaller black holes give off an energy called Hawking radiation, which would actually evaporate away a lot of smaller black holes over the course of, a certain amount of time, and that there wouldn't be any black holes that would be left over at this point in the universe that would be that small. So there is always a small possibility, but there's no way you'd be able to explain why that other planet would be a black hole at all. So to me, it doesn't make any sense. I don't know if either of you want to add to that.
Okay, so we still have lots of questions. We're not going to be able to get to all of them, but there is one person who's asked several questions and we didn't get to any of them yet. So I'm going to do one more question from Seiwan, I think the name is. And the question is, since all objects in the universe are in motion, do cosmologists have to correct images of large objects such as galaxies for time?
So I can take a stab at that. So when we think of motion in the universe, or velocity as we think about it, we actually have to split it up, because there's two kinds of motion in the universe. There's one which is actually apparent, because it's just as the universe gets bigger, you might think that things are moving. You might think that galaxies are actually moving away from you, but really the distance between you two is just expanding as the universe expands. And so we call that the Hubble flow, the flow of everything just with the expansion of the universe. But then if you actually say, now, no, the galaxy is actually moving, maybe something is being attracted to something else, then we talk about its peculiar velocity. And peculiar means strange. It means additional to the overall expansion. And that peculiar velocity is actually telling you something about, is Andromeda is attracted to our own galaxy. And so relative to the expansion, it's actually moving towards us. So it has a peculiar velocity. And that's a really good question. Not only do we do have to correct our observations for the peculiar velocity of these additional galaxies, if we can measure it. And in addition, some of what we can do, and in fact, this is what one of my graduate students, Anita Bahmaniar, is doing, we can actually use the measurement of the peculiar velocity of the galaxies to tell us something about how the universe is clumping. Because if we can see that galaxies are moving towards each other, that tells us something about the gravity between them, and therefore the mass between them. And so we actually can turn a bug into a feature. So.
Ilana, did you?
Oh, yeah. Well, and also astronomers do have to take into account like the motions of everything that's happening in our own solar system and of the sun around the galaxy, all of those measures. So I feel like I remember hearing a story of some of the first measurements of the cosmic microwave background, where, if you look at it just straight on, you actually notice a slight red shift and a slight blue shift of the entire cosmic microwave background. And that's due to the rotation of the Earth. And then also there's one due to the rotation of the Earth around the sun, and then also due to the rotation of the sun around our galaxy. So you do have to take into account all of those motions as well when you're looking at the cosmic microwave background. And you can correct me if I'm wrong, Renee or Abby, about that.
No, that's
awesome.
An example. Yeah, I mean, there's lots of places in the universe where like measuring things in time is like incredibly important. And like, I mean, for like one of the big discoveries recently also was like the actual like measurement of the black hole in the center of our galaxy. And one of the ways people kind of proposed that was possible is by looking at the stars moving really quickly around the center of our galaxy. So there's just like lots of stuff about the universe that we've discovered from those motions.
Okay, sorry, a little Zoom glitch there. Okay, so I think that brings us to the end of our time for this evening. So I'd like to thank all of our guests tonight, Dr. Ilana McDonald, Dr. Abigail Kreitz, and Dr. Renee Hlaschek. And I hope everyone has had a good time. Please join us again next week on Tuesday at 7 p.m. Eastern. And I just want to extend a special invitation to the aspiring astronomers in the audience this evening that if you have any other questions, I know there were a few in the chat we didn't quite get to, but if you have any other questions about, career paths in astronomy or how to navigate becoming a scientist, things like that, all of our addresses are on the Dunlap Institute website. So that's dunlap.utoronto.ca. I think we would all be happy to be in touch with you and help you get those questions answered if we didn't get them all tonight. So thank you very much, everybody, and we'll see you again next week. Bye for now.
Bye, everyone.